So after we talk about the basic format for a standard form quadratic function and how these values of a, h, and k relate to different qualities of the parabola, let's look at an example of one here. Okay. The more information we can glean from the function itself, the deeper our understanding is going to be of how quadratics behave and what these parabolas look like. Okay. So that's really the focus here. First thing we notice when we look at this standard form quadratic, okay, we've got the squared outside these parentheses. Okay, you would be able, I would assume, based on if you remember the work that we did on transformations, you should be able to sketch where this parabola would be. Okay, and we don't necessarily have to go in this order. In fact, I think we should start with the vertex. Now, the vertex of this parabola, okay, when you look at standard form, this is a, this is supposed to be x minus h squared plus k. That's a k. My tablet is sort of acting oddly today. When you look at this and it says x plus 5, keep in mind that x plus 5 could be rewritten as x minus negative 5, right? So our h value is negative 5. So in the vertex, the x coordinate is negative 5. The y coordinate is exactly matches up with whatever we have out here. If it's a positive, then this is a positive, right? If it's a negative, it'd be otherwise. So we know that the vertex is at -2, or excuse me, -5 and +2. We could put that somewhere like this. Okay. We also know that based on the leading coefficient, we know that this graph is vertically stretched, and we know that it is flipped over or opening down. Okay, so whereas a normal parabola would be here, or an x squared parabola would be here opening up, this parabola is here opening down, and it is thinner than normal, right? And this is all relative based on how we draw this, but we have a semi-accurate sketch of what this looks like. Okay, a couple of things you want to remember. As far as the vertex is concerned, okay, if you know the leading coefficient and you know the vertex, you're going to get asked quite a bit to maximize or minimize quadratic functions. Okay, so if we have a parabola that's opening down and we know where its vertex is its relative max. Okay, and if the parabola were opening up, its vertex would be its relative min. So the relative max is y equals 2, and it occurs at x equals -5. All right, keep that in mind. You're going to be asked for that on some of these homework assignments. All right, the vertex is where the relative min or max is, and that's determined by whatever direction the parabola is opening. Okay, this also plays an effect while we're here on the range. Okay, now the domain, right? I guess we could put this in there. Because this is not a fraction, because there are no radical symbols, we don't have to worry about excluding values. The domain of a quadratic function like so is always going to be all real numbers, right? That's just kind of one of those throwaway things. We know that because it's either going to go down and to the left forever and down and to the right forever, or up and to the left forever and up and to the right forever. So we have an infinite domain here, okay? But the vertex plays a big part in the range. So if this vertex is at -5, 2, which is here, and it's opening down, this is a value of 2. Remember that when we do the range, we always want to start at the lowest point. Well, a parabola that opens down, its lowest point is -infinity. And then we're supposed to trace this until we get to its highest point. Its highest point is going to be the y coordinate of its vertex. Okay, so the range terminates at -2, and if it terminates at -2 and we actually have a point, there is a point here that has the coordinates -5, 2, then we can include this with a bracket, right? Remember, we never use brackets with infinity. We use brackets with real numbers like so when we want to include that, when there's actually a point there. Okay, so the vertex tells us quite a bit about the rest of this graph. Okay, Last but not least, one thing you're going to be asked for is the axis, or this is sometimes referred to as the axis of symmetry. Okay, and you'll notice that these parabolas are symmetric, right? The axis of symmetry is this line, which passes right through the middle of the graph. Okay, and sometimes we use this to locate other points. Like, parabolas are not lines, so they don't have constant rate of change. All right, but if I have a point right here, I have a point that mirrors that on the opposite side of the axis of symmetry with that same y coordinate, right? And this distance is the same as this distance for those 2 points. So that's why knowing the axis of symmetry and using it as a mirror to find points like so that are laterally on the same level, it comes in handy from time to time. We'll just put it at that. Okay. One thing you want to remember about the axis of symmetry is that it is a line, and it is a vertical line. And vertical lines in the coordinate plane are referred to as x equals, and then whatever that number is, right? Well, if it cuts this parabola in half, that means it has to pass through the vertex. So another point of information, another piece of information that the vertex tells us is where the axis of symmetry is, right? It has to have the same x coordinate as the vertex. So just like the range I'm sorry, that shouldn't be a -2. I apologize. I'm just now seeing that. Maybe you saw that before and you're like, -2? What? What's he talking about? Sorry about that. The vertex tells us the y coordinate of the range, and it tells us the y coordinate of the relative min or max. The x coordinate of the vertex tells us where the axis of symmetry goes. Okay, we'll do another video here in a second about locating the intercepts of this function.